Okay, now that we've talked about all of the different elements and we've solved a few of these problems, let's just review everything and let's solve 3 more problems. Now keep in mind, most of the problems we're going to solve, almost everything you need to do is going to be with a Cobb-Douglas. So this first problem we're solving right here is a Cobb-Douglas utility function. Utility equals x to the 0.3 power times y to the 0.6 power. So with this kind of problem, you're always going to be given a utility function, the price of x, the price of y, and a budget. So the price of x is 3, the price of y is 4, and the budget is 12. You're going to have to be very quick at setting up these problems and solving them. So you want to just go ahead and write down your 2 equations that we're going to solve in 2 unknowns. Equation 1 says write down the formula for the marginal rate of substitution for this utility function. So let's zoom in here a bit. So for the marginal rate of substitution, that tells this consumer how many x's they're willing to exchange for how many y's. We take the exponent on the x times y in the numerator. So it's going to be 0.3 y divided by 0.6, the exponent on the y, times x. Remember, if we do all the calculus, that's what it's going to simplify into. So this is a little shortcut. Now we set that equal to the slope of a budget line. The easiest way to find the slope of a budget line is the price of x divided by the price of y. So price of x divided by the price of y, $3 over $4. The first thing I usually do with this first equation before I do anything else is just see if there's a way to simplify it that makes it a little easier. This is not required, it just streamlines things for me. So when I look at 0.3 over 0.6, that's the same as 3 over 6, which is the same as 1/2. So personally, I would simplify this by rewriting it as y over 2x, or you could write it as 0.5y, a half y, over x. Or we could just leave it the same. I'm going to write it as y over 2x because that's the way I like to look at it. That's kind of the simplest way to me. Equals 3/4. Or we might rewrite that 3/4 as the decimal equivalent, 0.75. All right, so that would be fine as well. Lots of options. You do the way that's simple for you. Okay, so now we want to solve this for either y or x. The way I usually think about it is let's just solve it for y. So if we solve that for y, we're just going to be multiplying both sides by 2x. And so what we're going to end up with here is y equals 2 times x times 0.75. 2 times x times 0.75. So we're going to want to collect the 2 and the 0.75 together. So 2 times 0.75 is 1.5. So we could write 1.5x. So this is a very important equation we're going to use in a second. And it tells us that we're going to want to buy more y's than x's. If we were buying 1x, we'd want 1.5 times that, 1.5 y's. If we were buying 2x's, we'd want 1.5 times that, or 3 y's. So now we set up our second equation, which is our budget line. So the budget line equation just says price of x times x plus price of y times y has to equal our budget. We're spending our whole budget, in other words. So $3 times x plus $4 times y equals our budget, which is $12. And so now we just want to take the 2 equations we have. This is our simplified version of equation 1. Plug that into 2. So we're going to take that y is the same as 1.5x, and we're going to substitute that in for that y right there. And we have 3x plus 4 times 1.5x equals 12. So I recommend, as always, pause the video now and solve this equation for x, and then plug it back into this equation for y. And then what we want to do is figure out how much utility this person would get if we plug those 2 values of x and y back in here and see what utility level pops out. Okay? Take a minute and do that. All right, so we get 9x equals 12. X equals 12 divided by 9, which is 1.333333. We can just round that off to 1.33. And then we plug that x value into this equation where it tells us that how many y's we want is 1.5 times as many x's, and that gives us 1.99999, which really is 2. Now we know how much x and y we're going to have. Now we want to know the utility level, so we plug those two values back into our utility function over here. And when we plug those in, we just raise the x value to the 0.3 power, multiply it times 2 raised to the 0.6 power. I'm getting about 1.65 utils. So a little more than 1.5, not quite 2. So let's graph everything here to make sure that it looks like it's okay. We want to graph the budget line. So let's graph the budget line first. If we have $12 and we spent all $12 on X's, 12 divided by 3 says we could afford 4 units right here. And if we spent all $12 on Y, 12 divided by 4 would be we could afford 3 Y's at most. Let's connect those 2 points. And now let's graph our solution. So x is equal to 1.33, somewhere around here. Y is equal to 2. Looks like that's our solution. Now what we're looking for here is to see, number one, is our solution on the budget line? Is it something we can afford? Yes. Number two, does this solution look like it has the amount of utility we solved for? Is it bigger than 1.5 but less than 2? Well, if we look over here at our legend, 1.5 utils is the brown one here. And it looks like, of course, we can get more than 1.5 utils because we know we could get 1.5 utils if we selected either this point A or this point B. So there's going to be somewhere in between where we can get more than 1.5 utility. And this looks like it's somewhere close to the middle. It doesn't have to be in the middle, but it's somewhere in between point A and B, which is good. And lastly, I'm looking to see, remember these equations that we're solving. Equation 1 says this point needs to be where the marginal rate of substitution, which tells us the slope of indifference curves. So let's look at the slope of the indifference curves in the area here. So right here, the slope of the brown indifference curve looks like it's the same as the slope of the budget line, right? So if we graphed an indifference curve, and let me just sketch one. You don't have to do this, but if we were to sketch an indifference curve that's in between the two that we see, the brown and the blue one here, we can imagine that it might have a shape, right? It's going to have a shape very similar to the brown and the blue, but it's just going to lie in between those two curves. And we can imagine that, yes, we could have a tangent point where this budget line, this point just barely touches that gold indifference curve. Now, if our solution had been somewhere like, over here, we would know that that's the wrong solution. Let's label that C. That can't be right because it's not on the budget line. It doesn't look like the slope of the budget line and the slope of indifference curves are anywhere close to the same in this region. We would know to go back and check our math. We've probably done something wrong. So again, you need to get very quick at solving this kind of problem. Cobb-Douglas utility function, x raised to a power times y raised to a power. And you need to get good at graphing them and checking your graph to see if it looks right. You're going to be doing this on the test several times. Now, just for those cases, you'll have a couple of homework problems where you might not have a Cobb-Douglas utility function. You have to understand how to deal with those. So here is a quasi-linear utility function, the square root of x plus y. And here we have extras are $3, Y's are $6, and our budget is $12. First, let's graph the budget line. It's okay to do that first before you do any of the other analysis. So let's go ahead and do that, and let's see if we can see an approximate answer here. So if we spent $12 all on X's that cost 3, how many could we afford? 4, okay. And if we spent all $12 on Y's, we could afford 2. And if we connect those 2 points together, we get something like that. So looking at this graph, it looks like we could get 2 utils here. Either by spending all of our money on X, or by spending all of our money on Y. Interesting. But given the shape of these indifference curves, there's probably another indifference curve that has the same kind of shape here that probably, I'm just going to guess here, we're probably going to end up erasing this in a minute, but probably has a similar kind of shape. So if I had to take a wild guess, our solution is probably going to be somewhere in this region. I know, not very specific, but just an initial guess. Let's go ahead and do the work, and let's see what the math tells us. So our 2 equations and 2 unknowns, marginal rate of substitution equals the price of X over the price of Y. Now the price of X over the price of Y is easy. That's going to be 3 over 6, or 1/2. But marginal rate of substitution, this is not a Cobb-Douglas utility function. We can't use that shortcut rule. So what we need to do is do it the long way. Remember that marginal rate of substitution, the way we get that is the marginal utility of X divided by the marginal utility of Y. So let's look at this utility function and find the marginal utility of X function. So the derivative of the utility function with respect to X is going to be the marginal utility of X. And we have 2 terms here. One has an X, the other one doesn't. So we know that that Y term is going to go away when we take the derivative with respect to X only. So we're really just looking at derivative of X to the 0.5. So that's going to be multiply by the exponent, subtract 1 from the exponent. That's going to be 0.5 X, and then we take 0.5 minus 1. So that's minus 0.5. And then to get marginal rate of substitution, we divide that by the marginal utility of Y. So here, if we take the derivative of this utility function with respect to Y, well, there's no Y here, that goes away. What's the derivative of Y with respect to Y? It's just 1, right? So the marginal rate of substitution is just simplify that, and it's just 0.5 X to the minus 0.5. So that's our marginal rate of substitution equals slope of budget line. Marginal rate of substitution equals price of X over the price of Y. So we just need to solve this equation for Y is what we'd normally do, but there's no Y there. So let's just solve that equation for X. Pause the video and do that real quick. If I want to get rid of that 0.5, multiply both sides by 2, which is the same as dividing both sides by 0.5, right? So if we multiply both sides by 2, multiply that side by 2, we're going to end up with just X to the minus 0.5 over here equals 1/2 times 2 is 1. What do we do to get rid of that minus 0.5 power? Well, the way to get rid of any power is to raise both sides to 1 over that power. Raise both sides to 1 over that power. So raise that to 1 over minus 0.5, 1 over minus 0.5. Now we could spend a long time thinking about what that means, or we could remember the rule. 1 to any power is equal to what? 1. Right, 1 to any power is just 1. When we do this on the left, we're just going to end up with X. When we do this on the right, we just end up with 1. So we're going to buy 1X. Now let's see if that makes sense with what we said in our graph. Yeah, it does, right? 1x, that's in this region that we were thinking about. And therefore, on the y, we should be getting about 1.5, right? Now, in order to figure that out, we're going to have to use the second equation, though. Equation 2 says the price of x times x, which is 3x, plus 6y equals 12. And if we plug in 1 here for x, we're going to do with 3 plus 6y equals 12. And subtract 3 from both sides. 6y equals 9. Y equals 1.5 exactly. Okay. So then the last thing we want to know is how much utility would we get? The graph is telling us that it should be more than 2, but less than 3. So let's see what we get here. Utility equals the square root of x, well, the square root of 1 is just 1, plus y, 1.5. How much utility is that going to be? 2.5. All right, so that's bigger than 2 and less than 3. Perfect. I trust that answer. I trust it. So there is an indifference curve, something like this gold one, not exactly. It's hard to draw one freehand. That's why I liked to get to the computer to do it for us, but there's our solution. Now I want to do one more problem here, because every once in a while, if you are using something like a quasi-linear utility function here, sometimes you'll run into a solution that doesn't seem to make sense to you. So we have to cover this last case. And this last case is when we get what we're calling a corner solution. So let's study this same utility function that we were looking at before, but let's change the prices. Instead of the prices being $3 and $6, suppose the price of x was 3, but the price of y went way up to $24. And let's suppose we had a budget of $24 as well. Let's set everything up. Now we don't have to redo everything from scratch because this is the same utility function as before. So when it comes to figuring out the marginal rate of substitution equation, we already know that. What was it last time? It was 1/2 or 0.5 x to the minus 0.5, and we set that equal to the slope of a budget line, $3 over $24. Okay, so 3 over 24. So there's our first equation. And just like last time, what we're going to want to do here is solve that equation for x because there's no y there. And then we're going to want to plug that into our budget line equation, which is $3 times x plus $24 times y equals $24. Pause the video, solve this for x real quickly, and let's see what we get. Okay, so after the first couple of steps, we've got x to the minus 0.5 equals 1/4. And remember what that negative sign means. That means it's x in the denominator. So let's rewrite that as 1 over x to the 0.5 equals 1/4. Now we could use a lot of different steps here to get the next part. What I want to do personally is I can invert both sides. Invert both sides. So if you ever have an equation with 1 over something equals 1 over something, you can flip both of them and you'll end up with x to the 0.5 equals 4. And we know that x to the 0.5 is the same as square root of x. We want to square both sides. So we're going to end up with 16 x's. Okay, so x equals 16. Now let's plug that in there for x, and we get 3 times x is 3 times 16 plus $24 for each y equals 24. 3 times 16 is $48 plus 24 times y equals 24. Pause. Think about what we see right here. This is a budget equation. And what this is telling us is that if we buy 16 x's, $3 each times 16 x's, we're going to be spending $48 on X. How much money do we have in our budget? 24. Something is gone strange with the math here. And what we're discovering right now is mathematicians sometimes have problems in economics. I swear, when I was at Duke, I went to school with a couple of people who had master's degrees in math. They thought getting a PhD in economics would be easy for them. And when they solved these equations, they just kept on going solving for X, and they never saw the problem because they weren't thinking about what it meant. They weren't thinking about what they were doing. But let's go ahead and let's see what pops out of this equation if we do it. Here we'd subtract $48 from both sides, and we're going to end up with 24y equals what? Minus 24. And so y equals minus 1. The math is telling us that we should be buying negative 1y and then buying 16x's. Normally this is something that we're not going to allow. It doesn't make sense. It's outside of what we think would make sense in a market to buy negative 1y. Now this could make sense if we really broadened our horizons. Buying negative 1y might mean that the consumer sells a y, and they use the money from the y they sold to buy more x's. We're not going to allow that in this standard kind of problem, but in the real world, I guess that could be possible in some circumstances. Let's graph everything and let's see what's happening here. So on this indifference curve map, I have the y's going down into the negatives so that we can see what's happening here. Let's graph the budget line. Let's see. So the budget line, we have $24. If we spent all of our money on y's, we could buy 1. So if we graph this budget line and we bought no x's, we could buy, that's no y's. So if we bought no x's, we could buy 1y. So that would be this point right here. If we spent all of our money on x's, 24 divided by 3, we could afford 8. So 0 y's, we could afford 8 x's. Now I'm going to draw this budget line, but I'm going to extend it like this to where it goes into negative y territory so that we can graph what we just saw here. This solution is suggesting that we should buy negative 1y and 16 x's, and that would put us right over here. But if we think that this is not possible, how does this consumer have a y to sell? Maybe that's not really something that they already have. What this kind of solution is actually telling us is this consumer, if they had a y, they would sell it. But if they don't have a y, they can't. So they want as little y as possible, in other words. So as little y as possible, we're only going to allow them to do the 0. That tells us that this point right here is the actual solution. Spend all your money on x. Don't buy any y at all. And we call this a corner solution. Now it's a corner solution because typically when we draw these XY graphs, we would cut it off. Just draw the first quadrant here where x's and y's are going to be positive, right? And if we did that, that purple point there would be at the corner. So this would be the corner where if they decided to spend all their money on y's, this is the corner we're looking at where they're going to spend all their money on x's. How do we know that's the solution? Because the mathematical solution says we want to buy more x's than we can actually afford. That's telling us spend all your money on x. We want to buy negative y. Okay, that tells us we don't want to spend no money on y. Buy no y's, right? So using our economics translation brains, the real answer, y equals 0. X equals as much as we can afford. X equals 8. Okay? What the math is trying to do here is look for what the math is telling the math to do, which is saying we want to look for a place where the slope of this red budget line is equal to the slope of an indifference curve, and that would be way down here in negative y territory. The math fails because we're not allowing our consumer to do that. What we're left with is just saying, okay, suppose this is the real solution, y equals 0, x equals 8. How much utility is it really possible for them to get? It's just going to be the square root of 8 plus 0. And the square root of 8, what do we get? About 2.83. So utility equals 2.83 utils. So again, just to summarize what we just did. Sometimes if you use something like a quasi-linear utility function, you can end up with a solution where the solution tries to tell you to buy a negative number of one of the goods. A corner solution means you maximize your utility by choosing to spend all of your money on either X or Y. But it's important that you pick the right one, right? The answer is not going to be spend your money on either X or Y. You have to figure out which one of those two maximizes your utility. Now in this case, let's just justify this. Suppose we looked at the other corner. The other corner would be right here, where we spent all our money on Y. We could only afford one of them. And if we only bought one Y, our utility would be 1, right? It's the square root of 0 X's plus the 1 Y we can afford. Well, that's not maximizing our utility. It's the other corner where we maximize our utility. So you can usually tell this is happening if your solution is telling you to buy a negative number of one of the goods. It's really telling you to buy none of it. But remember, this can only happen with indifference curves that can cross the x or y axis. This can never happen with a Cobb-Douglas utility function because, remember, with these, they never touch the x or the y axis. A corner solution would always give you 0 utils. So in this case, if we bought 4 x's and 0 y's, we'd end up with no utility. If we bought 3 y's and 0 x's, we'd end up with no utility because a Cobb-Douglas utility function is multiplicative. If you put in 0 for either of these, you're getting no utility, and that cannot be where you maximize your utility. So that wraps up this chapter 4 discussion. Make sure you're solid on this though. If you need more practice problems, I would be happy to provide. Because we're going to be using everything we're talking about here, mostly Cobb-Douglas utility functions, where we have these interior solutions though. An interior solution means you're buying some x and some y. That's always going to be the case with a Cobb-Douglas. So we're going to be using this kind of math. We're going to be using our marginal rate of substitution shortcut trick quite often. And we're going to have to be able to solve this kind of utility maximization problem very quickly, in like 5 minutes or less. Because in chapter 5, we're going to be using these answers to do some other things. So as always, if you have any questions, please let me know. I'm always happy to help. Other than that, good luck with your studies, and I'll talk to you later.